This lecture is about the product life cycle. In other words, the typical life cycle of a product. It could be a consumer product, a building product, or any other kind of product. Um, so I'm going to walk you through the steps of the typical product life cycle, and then we're also going to talk about ways to close the loop of a life cycle. In other words, have the life cycle of a material or product be less wasteful. So I'm going to start by walking you through this diagram. The first phase of a product life cycle is extraction of raw materials. Now, it takes energy to extract the materials. And in this process, there are emissions. Now, emissions might be particulate waste to the air, but emissions can also be liquid emissions or even solid emissions to water. And they also can be just waste that gets dumped on the land. So if you think about the mining of granite, for instance, a lot of material has to be removed from the earth to get down to the good granite, which might be anywhere from 40 to 80 feet underground. So emissions and waste are considerable at this phase, as well as the energy footprint of that. But and other raw materials don't have to be mined or extracted. They can be harvested. So it might be crops made harvested to make ethanol, or it might be trees cut for lumber or for paper pulp. That's all in the raw materials extraction phase. So then the raw materials get transported to the production phase. And I want you to note that there's transport all the way around this diagram because there's transport between every phase, and it's not a small thing, particularly if we're talking about heavy materials. And transport, of course, takes energy. The production phase is very often multiple steps. For instance, if you think about a panel of steel sheet metal, you have to make the steel in the production phase, and then that steel gets made oftentimes by a different factory into sheet metal. And it might still be a different factory that coats the steel with a galvanized coating to protect it and perforates it to make it perforated steel. You don't have to know what all these are, but I'm just trying to make the point that this is multiple steps. And at this phase, there is waste in the form of emissions to air, land, and water. Then the product, after it gets through the final production or fabrication phase, gets to the consumer. And very often it gets to a retail outlet and then the consumer, but that's all part of the consumption phase. During the consumption phase, there might be maintenance to take care of the material, or it might be a very short consumption phase, like that of a plastic bag that just gets discarded within 15 minutes of getting home from the store. But during this phase, there is waste, and there is a transportation burden. When the product becomes waste, it either gets released to land, or it might be incinerated, or it might be recycled back into the raw materials phase or into the production phase. It's also important to note that in the production phase, waste sometimes gets recycled back into other processes. So it's a complicated chart, but it's worth kind of studying this and looking at this and understanding it. Let's look at an example. This is birth to death of a plastic bottle. It takes about a quarter of a bottle's worth of crude oil to make the bottle. The oil is made into plastic pellets, then the pellets are heated up and expanded to shape the bottles. Then the bottles are sterilized, they're filled, they're capped, and it takes about 3 times the bottle of water to produce just the one bottle. The bottles are packed up into pretty heavy cases, put on trucks, and a truck full of plastic water bottles filled with water is pretty heavy. They estimate that the amount of resources it takes to transport these bottles is about 1 liter of gasoline per bottle. The store is stocked, someone buys it, drinks it, and discards it maybe within a matter of minutes. 77% of the time, it will become landfill waste. It might get landfilled, or it might actually get dumped into the ocean, which is very, very common. Um, and if it gets dumped into the ocean, chances are good that bottle will become part of the Great Pacific Garbage Patch, which was referenced in a lecture talking about the health of our oceans in a previous module. If it gets recycled, um, very often it may not be sorted properly, or if you left the cap on it, it won't be recycled at all because they're two different kinds of plastic and they don't want to commingle them. So then it will get landfilled from that. So even though we have what seems like a relatively high recycling rate here, ultimately most plastics are either downcycled or disposed of ultimately. So plastic recycling is not good. We'll talk more about that in a minute. So that's the life cycle of a plastic bottle. Note that it corresponds to the phases that we just talked about. So I'm going to talk about some of the phases in a little bit more detail here. Raw material extraction, of course, has substantial environmental impacts, including, when we're mining for things, the top level, the ecosystem is severely disturbed, and very often the biotic materials of the ecosystem, like the trees and the plants and the topsoil, are removed and oftentimes not replaced. We don't have a lot of regulations in this country about restoring mines and quarries, although some municipalities will restore them as public parks and that kind of thing. So raw material extraction has its own environmental burdens, but it also has its social impacts. First, I want to bring up the topic of environmental justice. And this topic has come up in many of our modules, but I wanted to define it for you here. Environmental justice is the fair treatment and meaningful involvement of all people in environmental decisions and regulations. Here in these images, in this example of the opposite of environmental justice. This is a map of the Para state in the Amazon. And the Amazon is a place that is often called the lungs of the earth. It is doing its yeoman's share of work to help us deal with climate impacts. But the more that we remove the Amazon or burn it or log it, the less help it's going to be to the world in terms of climate impacts. So what you see in this graphic here are land disputes and murders. So the yellow is logging that is happening intensively in the Amazon's deforestation between 2007 and 2016. And it's not a coincidence that the murders that are happening in the Amazon are correlated with the logging. There were 20,000 land disputes during this time and 1,700 murders. 80% of these land disputes had to do with illegal logging. We take tropical hardwoods out of the Amazon to use in decks, in patio furniture, as siding for houses. Our most durable lumber that we use in construction of these structures is tropical hardwood, but we have to stop using that because of these social justice and environmental justice violations that are happening in the Amazon. What typically happens is that there are protected lands for indigenous peoples to live on, and this is one of the indigenous people you see in the lower left of this image. Indigenous peoples are oftentimes driven off their land by people who are intending to illegally harvest the lumber. They are intimidated by murdering sometimes or injuring people. They move off their land, the poachers move in and illegally harvest trees and make thousands, if not millions, from those actions. So there are some social impacts of raw material extraction that are substantive. That's just one example. Manufacturing and fabrication is another phase of the process. And as I mentioned before, oftentimes it's multiple phases where fuel is used Raw materials are used and transformed during this phase, and waste is created. Here you see on the right molecular waste to the air, but very often there is substantial solid waste that is sometimes recycled back into the process. An example of that is when they make lumber, there is wood waste. That wood waste gets burned to power the equipment to process the lumber. So that's a good way to recycle the waste back into the process. And as long as the pollution control equipment on the burning of the waste is good, it's not that big of a problem to recycle waste in that way. But there are social impacts as well. It is not a coincidence that many of the most polluting industries are located in areas where marginalized populations live. This is Cancer Alley in southern Louisiana, where some of the poorest people in our country live. These are vinyl chloride plants. Vinyl chloride is the main ingredient in PVC, which stands for polyvinyl chloride. And PVC is everywhere in your life. It's in your shower curtain. It's in the rubber ducky that might be floating around next to your bathtub or in your bathtub. It's in the flooring in your kitchen. It is in the tabletop in your conference room or your breakfast room. It is a very ubiquitous material in our built environment, used a lot in construction and in furnishings. Unfortunately, PVC plants release dioxin, which is a known carcinogen and a known mutagen causing birth defects, into the air. And that dioxin falls on these communities, and hence the name Cancer Alley for this part of our country. These are huge social impacts, but the people who live in these areas may be aware of them, they may not, but they can't afford to move. So manufacturing has impacts like this all over the country, but this is just one example. The next phase of the life cycle, and it's not really a phase, but transportation happens in all phases, between all phases of the life cycle. This is a chart showing the carbon footprint in grams per ton of material transported of freight. So for instance, a large ship, a cargo vessel, has a much smaller carbon footprint than air freight. Trucks are more efficient than air freight, but not as efficient as boats. And what's not shown on this graphic is rail travel, rail freight. And rail freight is very similar to an efficient cargo vessel. So it's a very, very efficient way to distribute goods. But transportation has a substantial footprint when we look at the overall footprint of our products. So the use phase it can be short or it can be long. And these are some of the expected use lives of typical products. So plastic bags, plastic grocery bags are expected to be used for 3 weeks. And the use phase, of course, includes everything from the retail outlet to the consumer. Most consumers don't use plastic bags for even 3 weeks. Food containers, 2 months, clothing, 4 years. Probably a lot of the clothing that we use doesn't last for 4 years. Refrigerators, 11 years. Wood decks, 15 years. And I want to say just a word about wood decks. You know, people say, oh, wood, it's a renewable material, but it's really not if we only use it for 15 years because it takes far longer to grow the tree from which to harvest the lumber than 15 years. So this graphic on the right is showing the life cycle of plastics in the environment. So if a plastic bag was just put in a landfill, it'll probably break down in 20 years. If a disposable diaper was put in a landfill, estimates show that say that it will take 500 years to break down. Now, we haven't had disposable diapers for 500 years, so we don't know that for sure, but that's the estimate on this. Plastic water bottles, 450 years. So one of the things, of course, we're going to talk about is prolonging the use life of our products and materials. Unfortunately, our manufacturers and our product designers have some concepts to get us to use more of their products more often. There's two concepts: planned and perceived obsolescence. And basically, these are a policy of producing consumer goods that rapidly become obsolete, so you have to buy more. And this is achieved by changes in design, termination of the supply of spare parts, the use of non-durable materials. All of these things are either planned or perceived obsolescence. So let's look at the phone example. You might have an iPhone 5 and your friend has an iPhone 8G or Max, or I forget what the big one is called. And you say, wow, that's a cool phone. It's so big. I love it. I want that. And so you go get your 8G, and then you say, oh gosh, this is so big. It falls out of my pocket all the time. I think next year I'm going to go back down to a smaller model. But then the really big one comes out and the screen is so big that it cracks easily. And you say, oh, I'm just going to get a new phone rather than pay to get my screen fixed because I'd like to have a smaller phone. So it's the idea of somewhat planned obsolescence, but it's also perceived obsolescence. Your friend has something that you want. Your car looks like an old style of car. You'd rather have a new style of car. Your high heels are thin, and this year the style is that your high heels should be fat. Those are all perceived obsolescence, but planned obsolescence happens. And as much as I think Apple is generally a good corporation, they do planned obsolescence as well. And other cell phone companies do as well. So we end up with a lot of e-waste as a result. So let's look at how our waste is characterized. This is from the United Nations Environmental Program, showing the percentages of waste in the US, which is the orange colors, and in Germany. Similar amount of paper and cardboard waste. Germany has far less organic waste. So they either do a better job of grocery shopping and don't waste all of the food that we in the US waste, or they do a better job of composting. We have less waste than Germany. Germany has greater plastic waste than us. Textiles, it's a little different. Glass, it's very different. Metals, it's different. So this is by percent of total municipal waste. And this is from 2005. So it's a while back, but I think it's pretty similar still. So even at this phase, we have social impacts of waste. E-waste is a huge environmental health concern, but it's also a human health concern. Although some of our technology companies are starting to take back their e-waste and reuse it and recycle it safely, the majority of our e-waste, phones, CD players, televisions, computer screens, computers, the majority of this gets shipped to countries that have fewer regulations about e-waste recycling and e-waste safety. They have fewer worker safety regulations, and consequently, millions of people are exposed to the toxic components of our e-waste, which would be heavy metals that are persistent bioaccumulative toxins, very often hazardous chemicals. And so they're recycling them sometimes in situations like you see here that are not safely regulated. I mean, this person isn't even wearing gloves. This kid isn't even wearing gloves. These people are wearing gloves and masks, maybe a little safer, but still a lot can get absorbed through your skin. So there are some substantial social impacts of waste. So this chart is showing us how different countries dispose of their waste. The blue color is landfill. You can see in the US, we landfill the majority of our waste. Mexico landfills almost all of their waste. And it's pretty typical for some of these countries to landfill a good bit of their waste, although some of the Northern European countries are doing better with this, especially now that the EU has more regulations surrounding waste. The yellow color is incineration, and this is where waste is burned. Sometimes it's just burned to get rid of it. Sometimes it's burned for energy recovery. So in Northern Europe, particularly Sweden, they have pioneered this technology and actually pioneered a lot of technology that makes this pretty safe, the incineration. Um, and they recover energy for powering various things from that burning and incineration of waste. But that waste takes a resource and it downcycles it so that it's just ash. And maybe energy is derived from it, but the actual resource is compromised and beyond usability for the same type of use. So yeah, for instance, if you burn a water bottle, all you have is ash and a little bit of energy from it, and that's not the best use of waste. Composting is strong in certain European countries, in Italy, in Austria, in Spain. Composting very often leads to a very valuable resource, which is fully composted material that can be used in agricultural settings or in people's gardens. So that's a great way to take biological waste, food waste, and that kind of thing, and make it into something very valuable. Lastly, the green is recycling. And the US does okay in recycling. Some countries are doing better. South Korea is doing a lot better. Sweden is doing a lot better. Austria is doing better. Ireland is doing better. Our recycling systems are not very strong in the US. They're strong in areas where we have limits on what can go into the garbage. So for instance, in California, it's illegal to put construction waste into a landfill. It has to be recycled. And that's one of the main things that's kind of bumping our recycling rate up. It's not consumer responsibility, unfortunately. So plastic is a particularly problematic material to recycle because there's so many different kinds of plastic. You remember plastics have numbers. Only certain numbers can be recycled. If they're commingled, for instance, if you throw away your plastic water bottle, which is one kind of plastic, with the lid, which is another kind of plastic, the whole water bottle will get thrown in the trash. Nobody's going to take the time to unscrew the cap and recycle them. So there's a lot of problems in plastic recycling. There's some toxicity issues in plastic recycling as well. For instance, PVC is a plastic that I just talked about. It can theoretically be recycled, but when it's heated up, it releases the dioxins, which are toxic to any of the factory workers that are not protected from the release of the dioxins. So most of the time, PVC is not recycled. So you can see our woefully small plastic recycling rate. For the most part, we landfill it. Sometimes we combust it for, we burn it, incinerate it for energy. Most of the time, this recycling rate is very, very low. It's very inefficient. So let's look at this chart, which is showing the amount of material needed to make new and recycled products. So what's being shown here, let's look at aluminum right here as an example. This is the material and air needed to make new aluminum. And this is the amount of water needed to make new aluminum. That's substantial. Remember, when we talked about water conservation, we said we'd look at water conservation and water use in manufacturing, which is substantial. We also talked about it in the food module. When we recycle aluminum, it uses 97% of the material as new aluminum and just a fraction of the water to make the recycled aluminum. So that's really substantial. It's less substantial in the plastics industry, not as much savings. It's substantial in the paper and the cardboard industry, and not as much so in the glass, although 43% less material is used to make recycled glass. So you can start to see the benefits of recycling. But you might say, well, that's not the best benefit of dealing with waste. So this is called the waste hierarchy, and this is a very common hierarchy to illustrate the best use of our waste. And at the top of the hierarchy, in other words, what we ought to be doing mostly is preventing waste. So instead of recycling that disposable water bottle, let's not use a disposable water bottle. Let's use a reusable water bottle and prevent waste. Let's use reusable grocery bags. Let's reuse a piece of lumber that we take out of a building in a new building without recycling it. Or better yet, let's rehab the existing building and not tear it down at all and reuse it for something else. That's all prevention of waste. We might prepare the waste for reuse as we design the product. And I'll talk to you in a minute about an idea called designing for disassembly. That's designing for reusing the materials. We can build buildings to be able to more easily take them apart when at the end of the building's life. So recycling is kind of down here on the hierarchy. Recycling is not as ideal as prevention of waste or preparing and reusing materials. Recovery is the energy recovery that I was talking about, the incineration of materials to gain some energy. And then at the bottom of the waste hierarchy is disposal. And the ideal goal would be to have very little things that we actually dispose into a landfill. So when we start to think about ways to do things differently, we can recognize that right now we have what's called a linear economy. And basically a linear economy is where materials create waste after use. So we take the material resources, we make something with it, we use that thing, and then we dispose of that thing. That is a linear economy. That is a linear life cycle, right? We want to get to the point of a circular economy. And this is where materials are collected and reused after each use. So we might have collected materials that we transform into a reuse of some kind. We make a new product with it. We use the product, we collect the product, we transform it again, we reuse it again, we make something else with it, or we make something. So that's the kind of the glass example that I showed you earlier. The concept of designing for disassembly supports the circular life cycle that you just saw. This is a chair called the Mira chair by the office furnishings company Herman Miller. Each component of this chair, and you can see there are many components, can all be reused. These casters that the chair sits on, those can be taken off and reused on a new chair. The seat back, whoops, sorry about that. The seat back can be reused on a new chair. The hydraulic system for raising and lowering the chair can be reused, or the component parts of that hydraulic system can be reused. So this chair was designed to be disassembled and reassembled, some of the parts, in different ways, or at least for the parts to be recycled at the very least. That's called designing for disassembly. So just getting back to this idea of closed loop flows, closed loop material flows. This is the idea that the glass factory uses recycled glass to make new glass for consumers. It's collected, it's transformed, it's reused in new glass. And this is a closed loop life cycle. Raw materials, of course, have to start the life cycle. But ideally, we wouldn't keep pumping raw materials into new glass bottles. We would keep recycling them. And there will be some things that are disposed of at each phase of this life cycle. But in an ideal world, we'll close this loop. And you will hear in some of the TED Talk and the other readings that waste from one process is conceived of as food for another. So if we look at this on a large scale, we could have something called industrial ecology. And this essentially conceptualizes the industries as a human-made ecosystem that operates in a similar way to natural ecosystems. In a natural ecosystem, waste is food for another process. So a tree falls down in a natural ecosystem, all those little decay organisms get in there and they eat the tree, and they eat they break down and help the tree decay. The waste from those organisms becomes soil. So that's what this is meaning, is that waste from one process is food for another, or a byproduct of one process is used as an input for another. So let's look a little closely at this. Let's look at a farm. Here's a farm. The organic waste is sent to the biogas plant. Biofertilizer, some of the byproduct from the biogas plant becomes fertilizer for the farm. Grain from the farm gets sold to the ethanol plant. The ethanol plant makes ethanol to power the ships or to power a chemicals plant. Some of the fodder, which is the sort of solid waste from the ethanol plant, gets sent back for use on the farm. Here we can look at a forest where the biomass from the forest goes into paper and pulp production. The sludge from that goes into the waste processing plant. Waste fuel is derived to power the power plant. Biomass residue from the forest goes directly to the power plant. This is an example of industrial ecology that is happening in Denmark. It's a concept that's happening at a very small scale, even in the United States. But I think industrial ecology envisions that there would be no waste, that the waste would always be food for another process. And so that's, I think, what we're talking about when we talk about closing the loop of life cycles. So some of the readings that you'll be doing with respect to the Cradle to Cradle organization and the TED Talk that you'll be watching talks about closing life cycles. They talk about both the biological cycle and the technical cycle. So the biological cycle uses biological nutrients as food for plants. Plants get harvested and produced into a product. Maybe it's a cotton t-shirt. The cotton t-shirt is not treated with any chemicals that doesn't allow it to biodegrade eventually. And the biodegradation then produces biological nutrients, which feed plants, which are produced into another product. So that's a closed loop biological cycle. The technical cycle might have technical nutrients, which might be plastics or heavy metals or other kinds of metals. They get produced into a product, which might be, say, a computer screen. That gets used. Once it's been used, perhaps the company that produced it takes it back, disassembles it, like the chair that we just saw, and gets reassembled into another product and gets reused again. So that's a closed loop technical cycle. So I'll leave you with this, and I hope you'll pause here and study this, but the idea of closing loops leads to the sort of larger idea of a circular economy. Now, this is actually being practiced in some parts of Northern Europe on small scales. But the components of a circular economy are renewable energy instead of using fossil fuel energy, using natural capital to the extent that we can. In other words, using trees and plants as resources and not depleting non-renewable resources. Some new revenue models are the idea of the producer take back. In other words, that chair is designed to be taken back by the firm, Herman Miller, that made the chair. And so instead of buying the chair, the people who are going to use it, the office that's going to use that chair, might actually just rent it. And so when they're finished with it, they give it back to Herman Miller. The company Herman Miller takes it apart, designs new products with it, and puts it out again into use after it's designed and produced. And eventually it might get taken back and components will get reused. Components from the production process might get recycled. The chair, the next chair or the next component of that furniture company might get recycled into new products. So that's the idea of the circular economy. And that means that there needs to be a supply chain collaboration between all of these different industries and all of the players in the supply chain for a particular product. So a circular economy like this, lastly, will give much more value to reuse and recycling materials. So if we weren't able to just throw it in a landfill and obtain new cheap materials, our recycled materials would be worth a lot more. And in plastics right now, one of the primary reasons we don't recycle a lot of plastics is that new plastic is so cheap. It doesn't make sense to set up the infrastructure in a big way to recycle plastics because we just keep using our crude oil to make new plastics. So, so this kind of circular economy would give much higher value to recycled and reused materials. So these are all kind of forward-thinking, interesting ideas, but watch for these as we move through this this module. Thank you.